Today I'm going to show you a real proof of concept vulnerability in an Adonis.js application. But before we start, a quick reminder, this demo is performed on a vulnerable web application running on my own local host, strictly for educational purposes. So please don't try this on any real website without proper authorization. Now let's begin. First, I visit my target application in the browser, and as you can see, everything loads completely normally. No errors, no warnings, nothing suspicious at all. The home page looks clean and functional, which is exactly how most vulnerable applications look in real life. Next, I navigate to an upload route that the application provides. This route allows users to upload files to the server, and the interface is very simple. I choose a file, click upload, and the file gets stored on the server. At this point, nothing seems wrong, but this upload functionality is exactly where the vulnerability lives. Before uploading anything, I open my intercepting proxy, in this case Burp Suite, so I can capture and inspect the HTTP request. Now I upload a file. And the request gets intercepted in Burp Proxy. Before exploiting anything, let me explain how this vulnerability actually works behind the scenes. The attack starts when an attacker crafts a malicious multi-part form data POST request to the upload endpoint, usually something like an upload route. Inside this request, the attacker includes a file field with any arbitrary content. It could be HTML, JavaScript, TypeScript, or even plain text. But the key part is the file name parameter. Instead of a normal file name, the attacker supplies a file name containing path traversal sequences. On the server side, the application is using a vulnerable version of the Adonis.js body parser, and this parser processes the multi-part request and extracts the file name exactly as it is sent by the client. There is no sanitization, no normalization, and no removal of dangerous characters. That means path traversal sequences, absolute paths, and directory escapes are all accepted as. Now, if you look at the upload handling logic on the screen, you can see that the application simply takes the uploaded file object and moves it into the uploads directory using the file name provided by the client. There is no validation or transformation happening here. The server fully trusts the client controlled file name. Because of this, the underlying file system resolves the path using normal path resolution rules. So, when a file name includes traversal sequences, the final resolved path can escape the intended uploads directory. With enough sequences, the attacker can write files anywhere the server process has permission, including the public directory, application source files, or configuration files. Now let's test this practically. In Burp Suite, I modify the file name parameter and add a traversal sequence to move one directory back, then I forward the request. The server responds successfully, meaning the file was written without any errors. When I reload the website, you can immediately see the impact. The uploaded content is now rendering directly where it should never exist. That confirms we've successfully written a file outside the uploads directory and achieved arbitrary file write. Now let's escalate this into full remote code execution. For this step, I prepare a malicious file that defines a new route and executes system commands passed through a request parameter. You can see this file on the screen. It's designed to take input from the URL, execute it on the server, and return the output in the response. I upload this file again, intercept the request in Burp Proxy, and modify the file name to traverse directories. At this point, understanding the framework structure is important. In an Adonis.js application running in development mode, route definitions live inside the start directory, while uploaded files are normally stored under the public uploads directory. To reach the routes file, I traverse back the required number of directories and then point directly to the routes file location. Because the application never validates the file name, this traversal works perfectly. I forward the request and let it complete. At this moment, the malicious file is written directly into the application's routing system. Now I simply open the browser and visit the new route that was just injected. I pass a command parameter in the URL, press enter, and immediately the command output is returned in the response. I can change the command to things like checking the current user or system identity, and each time the server executes it. That's full remote code execution, achieved purely through a file upload vulnerability combined with path traversal. Finally, let's talk about how this issue should be fixed. First, always keep framework dependencies updated, especially core components like body parsers. Second, Never trust client-provided file names. Always generate safe file names on the server side. Third, enforce strict directory boundaries and reject any file name containing traversal sequences or absolute paths. And finally, run applications with minimal file system permissions so that even if a vulnerability exists, its impact is limited. And that's it for today's breakdown. Thanks for watching. I hope this helped you understand how real-world file upload vulnerabilities work in modern frameworks, and I'll see you in the next breakdown.